Hello, everyone. My name is Han. Thanks for the introduction. So let me acknowledge my co-author first. This is a joint work with colleague Pohan Namo, Xiaochen, and Professor Sunis and Professor Ramesh Govindan. And the title is AutoCast, Scalable Infrastructure-less Cooperative Perception for Distributed Collaborative Driving. So nowadays, autonomous driving cars are equipped with LiDARs, sensors, cameras, and they're using this to sense 3D environments, but they're all limited by line of sight. So for example, in this LiDAR I'm showing here, the car can sense everything around it, but nothing behind the truck in front of it. So the problem is occlusion. In fact, this is a really critical problem. It affects your driving safety, driving behavior. So here is a small video showing how an autonomous driver reacts to exactly the same situation. You have a double parking sedan in front of you. And as we move, you can see some red fences in front of it. That's indicating a stopping point where the planner tries to stop, abandoning the planned path because it's not sure what's going on behind the sedan. So cooperative perception can solve this problem. The idea being that we can share what the front car can see to the car behind so that we can, the car behind can see through the obstruction. And the way is to wirelessly share the sensor data. So previous work, including AVR in MobiSys 18, F. Cooper in SEC 19, and EMP in MobiCom 21, have all demonstrated that this is feasible for small-scale experiments. For example, peer vehicles, when they are sharing, they can provide more vantage points for receiving vehicles so that they can provide enhanced visibility to previously invisible objects. And what this means, to better understand this, what it means to autonomous driver, here is some small video showing in action. So on the bottom, you can see the black sedan. That's the car where the controlled vehicle. And there's a red sedan rushing a red light. So by receiving the information from peer vehicles, the controlled vehicle can now slow down ahead of time and then pass through the intersection safely. This all sounds cool, but how can we scale this capability to every vehicle's in need? Suppose you have a pretty busy intersection like this, and H is trying to turn left, A is trying to go straight, but because of occlusion, H can now see A. So in this case, C can share A's information to H. And symmetrically, if C tries to turn left, I tries to turn right, H can share I's information to C. There can be more sharing happening. For example, F can share crossing pedestrians information on top to I and C. And a roadside unit can share traffic light information to a car far away, like L. But you can already see there are a lot of interesting problems now. Like, how do we know which car should talk at when and talk about what to whom? So there's a bunch of questions to make this happen. So on a very high level, to scale cooperative perception, we need to scale it to dense traffic scenarios with very limited wireless bandwidth and achieve low latency to meet real-time driving decision deadlines. So to address these challenges, AutoCast makes several contributions. We included a spatial reasoning module to decide which object is of interest to which vehicle by analyzing the occlusion relationships and visibility to receivers. And then based on this, we can decide the object's relevance to each receiver. And AutoCast also has an orchestration and scheduling module to coordinate this sharing among vehicles and to enable vehicles to share metadata and then schedule the transmission to optimize the utilization of the wireless bandwidth. Finally, AutoCast has also included sensor fusion and trajectory planning to leverage shared vision in real time. The whole stack is optimized to meet the latency deadlines. So before I dive deeper into the contribution, let's give you a 100,000 foot view of the architecture. Suppose we have 30 frames coming in to the vehicle, And the first module is spatial reasoning. So the vehicle will process the LiDAR frames and analyze detected objects and the occlusion relationships. And then we can exchange that metadata to other vehicles through a control channel. And upon aggregating all those metadata, we can schedule the transmissions for each vehicle. And following that schedule, we can exchange sensors through a data channel. And then by merging all those sensor data, we can finally make a trajectory plan. The trajectory will be executed on the control module. So the whole architecture can be divided by two planes, a data plane and a control plane. The data plane includes spatial reasoning and trajectory planning, and of course, sensor exchange. The control plane includes metadata exchange and distributed scheduling. Okay, so let's dive deeper into each of them. So first of all, object of interest. This is the spatial reasoning module. Suppose we have a red car where we have a LiDAR mounted on it, and the LiDAR can sense all the environments around it. You can already see the blue cars shown on the yellow points. So to extract roadway objects, we can do a voxelization of the point cloud and analyze and classify each graze as empty, ground, or object. And to analyze the visibility, so this is the object's graze, which is above the ground and not empty. And to analyze the visibility, we can just track the empty graze behind the objects so that we know which area is invisible to the ego car. And if every car can decide that information, we can share their information through the beacons, the control message. And then every vehicle knows the global occupancy grade. Then they know whether their detected objects is relevant to other people, to other vehicles. And based on the visibility and the other people's trajectory, we can decide whether is this relevant to some of the receivers or none of them. So I'll come back to this with more details when we talk about scheduling. So the next step is orchestration and scheduling. So first, we need to coordinate the transmission of those metadata. So we designed the vehicles to send periodical beacons, which we call a control message, which share their pose, their trajectory, their detected objects. And by sharing the detected objects, they are implicitly sharing the invisible area because with the pose and the object's location, the receiver can trace a line to the object and decide the areas behind it to be the invisible area. And once we aggregate all this information, the metadata from all vehicles, we can do a distributed consistent schedule. So let me formulate the scheduling problem a little bit. So suppose we have V vehicles and O objects. Each object can be shared via different representation. Let's say you have C classes representation. And let's define an indicator xijk being vehicle I trying to share object j in representation k. And let's also define the vehicle's interest as wpj, meaning vehicle P is interested in object j. So in this case, for example, A is not visible to H, so WHA will be 1. But since C can already see A, so WCA will be 0. As we said, based on the visibility and the trajectory from the beacon, we can determine this value. And then let's formulate the optimization framework. So the goal is to maximize the reward function of the total interest of the objects being shared. And you can see there's different P's, so maybe multiple vehicles is interested in object J. And each object is only needed to be transmitted in one representation. And the total transmission time of the objects scheduled should be less than the total time for the scheduling period. And this formulates the problem into a multiple knapsack problem. And the traditional solution takes, given a 40 vehicle, takes 10 minutes to find the optimal solution. And dynamic programming at PITAS is taking 3 seconds. This is still too long because we want the scheduling to happen at least every 10 frames per second so that matches the LiDAR's income rate. So we come up with a heuristic. We rank all the objects reward. We rank up all the objects by the reward over the time. So that will send the objects with the highest reward and the shortest time to transmit. So this heuristic takes only 0.06 seconds. And you can see the performance here. The red triangles is the greedy heuristic. It matches almost the same with the optimal solution. Compared with the green dots, green triangles, which is the agnostic solution, which is a random scheduling, random transmission. And finally, we have also included sensor fusion and directed planning. I won't have time to cover this, but I'll show you some examples of the planner in the video demo at the end. So we did a thorough evaluation on AutoCast, including end-to-end scenario evaluation, scalability benchmark. We also validate with the V2V redos. And also we did some detailed analysis of the scheduling part, which analyzed the optimality, scalability, latency, and the staleness of the object. Also some sensitivity analysis about the impact of vehicle speed and the reaction time and the near-miss distance. Finally, the end-to-end latency and the profile of each module through the stack. So I'll talk some of the interesting results. Before I show the results, let's first dig into the evaluation scenario. We have designed 3 scenarios: overtaking, left turn, and red light violation. So these scenarios is specifically designed because occlusion could have a significant impact on the driving behavior. And in each scenario, if you notice, there is a black sedan on the bottom. That's the controlled vehicle. And there's a red sedan, which provided as the collider. And there's an orange truck provided as a occlusion. So if you see the point cloud shown here, there's always some occlusion. And the red dots are the shared points through AutoCast. So if you want to look in more detail, we can go through each example. For example, overtaking. So this is a control vehicle in the red circle. And the control vehicle trying to overtake the double parking truck, but unaware of the upcoming red car in the opposite direction. So it has to take a dangerous lane change maneuver to do the overtaking without knowing the potential collision. And in the left turn scenario, the control vehicle is trying to make a left turn, but there's also another truck trying to make a left turn in the opposite direction. And there is a red sedan behind that truck who is going straight. And without cooperative perception, the control vehicle could crash into the red vehicle. Finally, the red light violation. The control vehicle is trying to go straight through the intersection. And because of the occlusion of the truck trying to turn left, the collider is violating a red light. By the time they see each other, it might be too late to brake. So through these 3 intersections, we evaluated the scenario's outcome, shown the x-axis here, the safe passage, the crash, the deadlock, and the near miss. We compare our solution with 4 baselines: a single with no cooperative perception, EMP, one of the state-of-the-art edge-assisted cooperative perception, agnostic, random scheduling solution, and unlimited, sharing all the objects around it without any bandwidth constraint. So as you can see, the red bar is the AutoCast. AutoCast can eliminate all the crashes and undesirable deadlocks in all the scenarios, which can be incurred by other baselines. And here I'm showing the scalability results. So the previous results was broken down into 4 groups with different density of traffic, shown on the x-axis here, 5, 10, 12, 20, 40. And the 2 figures shows the safe passage ratio and the collider visibility time. As you can see, AutoCast scales gracefully for up to 40 vehicles with the near optimal performance compared to the unlimited solution. And only at the 40 vehicle density, we have some near misses. And we also validate the schedule transmission using V2V radios. We're using iSmartWave's DSRC radio here. You can see the front end in the red circle mounted on the car, and the box from iSmartWaves in the vehicle, in the green circle. And the right figure shows the schedule transmission in the blue lines and DSRC's transmission in orange lines. you can see the DSRC radio capacity can keep up with the scheduled transmission. Finally, this is the end-to-end latency. We profile each module's latency through the whole stack. And you can see the end-to-end latency is about 90 milliseconds per frame. So we can meet up with the LiDAR line rate. Finally, I'll show you a small demo how AutoCast can enable vehicles to drive on the dense traffic. You can see there are many things happen here. This is the left turn scenario. The Eagle car's trajectory is the planned path, and the trajectory of every other vehicle is detected and estimated. The trajectory is a 10 seconds receding horizon from green to blue. So you can see under dense traffic, AutoCast can still enable the control vehicle to see the occluded car to avoid the potential collision. So in conclusion, AutoCast enables scalable cooperative perception to dense traffic scenarios. It has efficient spatial reasoning module to analyze object relevance to each receiver. It can coordinate and optimally schedule the transmissions and enabling more informed planning and control to avoid a crash. So the entire code stack is open source to the community on GitHub. It has the spatial reasoner, the scheduler, the planner, and the scenarios. Feel free to play with it and swapping any module of your design to test and validate. And with that, I can take any questions.